Chapter 6, Section 7. There's three main types of applications we're going to look at using these rational equations and proportions. The first one is problems involving work. And let's go at this example. They kind of derive what we're going to use for a strategy and how to write equations for this, basically by going through the process of kind of working simpler problems or throwing some ideas at it and see what happens, and hopefully we can get something out of this. Well, example one is that Brian and Reba volunteer in a community garden. Brian can mulch the garden alone in 8 hours. Reba can mulch the garden alone in 10 hours. How long will it take for the two of them working together to mulch the garden? Well, if we familiarize ourselves with this problem, they're going to say, well, let's try some things. Like if you work problems, often incorrectly translated into mathematical languages several ways. Well, first one I say, well, we could add the times together. 8 hours plus 10 hours is 18 hours. And this cannot be the correct approach, since it would take Brian and Reba longer to do the job together than it takes either of them working together. We could try averaging the time. So if you add the two times together and divide it by 2, it'd take 9 hours. Well, that still doesn't work, because Brian can do it faster or in less time than the two of them together again, so that doesn't make sense. If we assume that each person does half the job, that still wouldn't be right, okay? Because that's kind of like that one before. Let's look at how that comes out. If a person does half the job, Brian would be finished with his half in 4 hours, and Reba would be done with her half in 5 hours, right? So we'd end up with that 9-hour kind of thing again. So, which is more time than just Brian working on his own. Each incorrect approach began with the time it takes each worker to do the job. The correct approach instead focuses on the rate of work, or the amount of job that each person completes in 1 hour. So what they're going to do is, since Brian takes 8 hours, he does 1/8 of the garden in 1 hour. And since Reba takes 10 hours, she does 1/10 of the garden in 1 hour. So if they mulch together in 1 hour, basically they would have 1/8 of the job done by Brian and 1/10 of the job done by Reba. If we added those two things together, we'd end up with 9/40ths of the garden per hour. So the rate are thus, they say, if Brian is 1/8 and Reba is 1/10, together they'll do 9/40ths of the garden in 1 hour. We are looking at the time required to mulch one entire garden though, okay? So, and that's what we don't know here. So let's look at how we're going to get that part. Well, this is a very nice table to look at, in the sense to say, let's start getting through this deal. Well, if in 1 hour Brian does 1/8 and Reba does 1/10, you get that 9/40ths. What happens in 2 hours? We get 9/20ths. 3 hours, I get 27/40ths. Well, if we make a fraction for the amount of hours, because that's what we don't know. Now basically, having this rate of the whole garden that they can complete per hour, we can basically come in here. Now I could keep going if I did this, let's say for each hour, I did 4 and so on. Eventually, if this ending fraction here ended up being 1, that means one garden is done. Just like what it says, 1/8 of a garden and 1/10 of a garden, or together they do 9/40ths of a garden in 1 hour. So we could probably keep doing this, but we want the ability to write an equation. So we're looking for this deal here. It says in T hours, or unknown amount of hours, what does Brian do? Well, he does 1/8 per times the hours, right? Or T in this case. Reba does 1/10. And together it would end up being the same thing. Here's both of them, and we'd end up with this 9/40 T. Well, what does this need to be equal to? We want that to be equal to 1, which is 1 garden in this case. So from the table we can see that T must be some number for which the fraction of the garden done by Brian in T hours, right? And the fraction of this done by, I forgot her name, Reba, right? Would be 1/10 times T. In other words, if we simplify this or do the multiplication, we get 2e over 8 plus t over 10 equals 1 whole garden, because we're looking at a situation. Just to give you some contrast for this, if we had this same situation and we knew that it took 8 hours for Brian to do 1 garden and Reba to do 1 garden is 1/10 of or 10 hours, we'd derive this kind of stuff. You know, I could do things like say, well, what if I wanted them to do the garden twice? Well, then this would be 2, and so on, because this really indicates that 1 garden. So to carry out this equation, now we have an equation with 1 variable, and we can solve that, and we end up with time. Okay. Now they really did a lot of work here to create this scenario. But it's really important to understand, how did I get here? Because just to have some random formula like this to say here's how you do work problems, I wouldn't suggest that. You may be able to memorize that for a quiz or a test, but it's not going to help you down the road much. Okay. To carry out the solve here, they kind of do a couple things. One of the strategies we have is to clear fractions. We use the LCD of 8 and 10, and we get 40. So you take 40 times both sides, and t equals 40 over 9. Okay? Which is kind of interesting right here, right? 9/40ths. Right? Okay? Or probably in this case you'd probably use a mixed number, because they're not going to say 40/9ths of an hour. We're looking for time. If you took ninths, you'd probably take that into a whole translation process of saying hours and minutes and stuff, but they don't do that here, so they just put it into hours. But I'll take that as an answer. 40/9ths hours would be the amount of time it would take both of these people to do this garden together. So let's look at this work principle. And they kind of summarize what we went through in deriving this, pretty much like a formula. If I have A, the time needed for big A or something to be completed alone by that person or a machine or whatever it is that does that thing, let's call that A. And then if I have B as the time it takes for this other person or machine to complete some work, the same amount of work, then time needed for both of these together will end up being in this type of equation. The time over A, the time over B. Okay. So if we have 1 hour, we can figure out how much work they do per hour, and we can create these kinds of equations here. Now these really are just equivalent equations. T over A plus T over B equals 1. Here they factored out the T, and in using like the distributive property, here they rewrote the fractional way of T over A is the same as 1 over A times T and 1 over B times T. And or I can have 1 over A plus 1 over B equals 1 over T. And this type here was kind of like, hey, this looked like that ended up being a reciprocal when we looked at adding those fractions together. But really that was about how do we get something that makes sense for these kinds of problems. So let's look at another work problem. The example 2 here says it takes Manuel 9 hours longer than it does Zoe to rebuild the engine. Now we're going to get into systems again. So we're going to end up with two equations. But if you don't understand that work principle, you'd be really lost trying to get one of these equations. So let me start over again. It takes Manuel 9 hours longer than it does Zoe to rebuild an engine. Working together, they can do the job in 20 hours. How long would it take each working alone to rebuild the engine? Okay, so now we start with, hey, we know how much time it takes when they work together. So these steps here, they keep showing them with word problems, is hopefully it gets so you practice this on each word problem. You know, unlike example 1 here, you know, they're making a comparison. Some of that is familiarization, as we say, have I ever worked anything kind of like this? They do this. They compare it to example 1. It says this problem does not provide us with the time required by individuals to do the job alone. So we will let Z equal the number of hours it would take Zoe working alone. And then we get this comparison here, which is Manuel takes 9 more hours than Zoe. So if we define the variable, a lot of times I say familiarizing this thing is define the variable, go back to the original and start reading this, and you'll start writing your expressions here. And that's what they're doing. So if I let Z equal the time for Zoe to rebuild an engine herself, then what would be represent Manuel? It would be 9 plus Z, or Z plus 9. That's 9 longer than Zoe. Okay, so we can translate these things using the same reasoning as example 1. We see that Zoe completes a job in 1 over Z. 1 completes this fraction of the job. So again, let's step back to kind of example 1 to try to, you know, fit this in here. Let's say I did know Zoe, it took 5 hours to rebuild this engine, and then what would she do in 1 hour? Well, she'd have 1/5 of the job done in 1 hour. Well, how many hours would it take Manuel to have rebuild an engine? If Zoe was 5, then Manuel would be 13. And if I put 5 in for Z here, I get 1/13 of the job, right? And so on. So I start trying to throw this together. I'm doing a simpler problem by throwing some numbers at it and saying what would happen when we understand how this work principle works. Okay? Well, with this I can get fractions of 1 over Z and 1 over Z plus 9. So we know that the amount of time in hours is 20 hours. Zoe completes Z 1 over Z times 20 of the job, because this is how much she does in 1 hour. And Manuel does 1 over Z plus 9 times 20. In other words, how much of the work are each one of these would do if this is the rate they do per hour, right? So they start fitting this thing together, and we end up with this equation of, or with this relationship of the 20 being the time we know it takes for each one of these, or these two, to do it together. So you take the amount of work done by Zoe and the amount of work done by Manuel here, which would be that times 20. So here again, here's the time over this times this fractional per hour rate for each person. And then it's going to add up to 1. That is one engine rebuilt in this case. So we carry out these, solve this. They do LCMs again. Least common multiple between these denominators here is z times z plus 9. So they do that multiplication and they end up with z plus 9 times 20 plus z times 20 and z times z plus 9 times 1 over here. So we end up with this trinomial, really. And the only way we can solve these things is to get them equal to 0, so we can factor and use the principle of zero multiplication. So they probably use grouping or anti-FOIL on this and end up with these two binomials. And when these factors are multiplied and they equal 0, then one or both of these has to be equal to 0. So you set each one equal to 0, solve, and we get z equals 36 and z equals -5. Now when we're talking about amount of work done, I don't think that there's going to be any negative work done. So we can throw out this negative one. And what does that mean? Well, 36 means that 1/36 of the job is done per hour by Zoe. Okay? So they start putting this back in here. And the number 36 checks, since if Zoe takes 36 hours alone, how long would it take Manuel? It would take 45 hours alone. Well, that sounds reasonable, that we got something that they would, if it took, those larger amounts of time, that if we put this together, they would take less time, almost less than half. And then we go back and we restate this thing. Well, 20 over 36 plus 20 over 45, does that equal 1? Yeah. And we get one complete rebuild, and we can state that it would take Zoe 36 hours to rebuild the engine alone and Manuel 45. Okay?